London 9 a.m. Your card is used at a coffee shop. Everything is fine. New York 9:03 a.m. The same card tries to make a purchase. Blocked instantly. Under 100 milliseconds. No human reviewed it. A machine made that call faster than you can blink. And it was right. Today we are going inside the fraud detection pipeline. This is one of the most sophisticated real-time machine learning systems in existence. And it runs silently on every card transaction you make. Before we look at how fraud detection works, we have to understand what it's optimizing for. Fraud detection systems operate under two brutal constraints, speed and accuracy. Speed means the decision has to happen in under 100 milliseconds before the payment terminal times out. Fraud detection has to complete its entire analysis, rules, models, graph lookups, decision inside that window, 100 milliseconds. For a system making decisions on hundreds of millions of transactions a day. Accuracy means the system has to catch fraud without blocking legitimate customers because both mistakes are expensive. If fraud gets through, the bank loses money. If a real customer gets wrongly declined, you lose trust, and often the customer never comes back. So this isn't just detect fraud. It's detect fraud fast, at scale with very low error rates. That's why modern fraud detection is not one model. It's a multi-layer pipeline. The first layer is the rules engine. The first layer of fraud detection is not machine learning. It's rules. Hard, fast, deterministic rules that run in microseconds. Examples of rules. If a card is used in 2 countries within 3 minutes, block it. If a transaction is 10 times higher than the account's normal spending, flag it. If the card is on a known compromised list, reject it. If the IP address looks like a proxy or a region that customer has never used, flag it. If a transaction at 3 a.m. in a location that account has never transacted, flag it. Rules handle the obvious cases instantly. They are also auditable and explainable, which matters enormously in regulated industries. When a regulator asked, why was this transaction declined? You want a clear answer and can point to a specific rule. Not a vague model score, a real rule. Rules are maintained by fraud analysts who study patterns in fraud data and translate them into logic. They are updated constantly as fraudsters adapt. A new fraud pattern appears in the data. Analysts write a rule to catch it. Fraudsters adapt again. It's an arms race. And many suspicious transactions don't look obviously bad. That's where the second layer comes in. Machine learning scoring. Rules catch the obvious cases. The interesting cases, the ones that look mostly legitimate, go to the ML model. The model sees hundreds of signals about the transaction. Time of the day of the week, merchant category code, that is MCC. Is this merchant type unusual for this account? Transaction amount, absolute and relative to account history, geographic velocity, how far from the last transaction and how much time elapsed, device fingerprint, is this the same device the account usually uses, browser or app details like OS version, screen resolution, language settings, session behavior, how did the user navigate to checkout, did they browse normally or go straight to purchase. This feature vector goes into a trained model, typically gradient boosting, XGBoost, LightGBM, or a neural network, trained on hundreds of millions of historical transactions with known outcomes, fraud or legitimate. The model outputs a score between 0 and 1. The probability that this transaction is fraudulent, low score means approve, high score means block. In the middle, send it to extra verification. The threshold is calibrated to hit the target false positive and false negative rates the business has decided to accept. Next comes the behavioral biometrics, the invisible signal. This is the layer most people don't know about, and it's one of the most powerful. Behavioral biometrics captures how you interact with the device, not what you do, but how you do it. Like typing speed and rhythm. How long between key presses? Everyone has a distinctive cadence when entering their card number or password. A bot enters characters at precisely regular intervals. Humans have an irregular rhythm. Mouse movement patterns. Humans move a cursor in curved, slightly unpredictable paths. Bots move in straight lines or systematic patterns. Touch pressure and swipe dynamics. On mobile, how hard you press, how fast you swipe, the angle of your finger, these are distinctive per person. Copy-paste detection. Legitimate users type their own card number. Fraudsters using a stolen card they have never memorized, often paste it. This is a powerful signal. Systems like BioCatch and NeuroID specialize entirely in this layer. Banks license these as additional signals feeding into their fraud models. A transaction might look perfectly normal by every other metric, but if the behavioral biometric says this doesn't type like the account owner, the risk score goes up significantly. So now the system has gone from simple rules to a much richer risk estimate. But there is still another layer because fraud rarely happens in isolation. That brings us to graph analysis. Fraud travels in networks. Fraudsters don't operate alone. They are connected. A single data breach compromises thousands of cards. Those cards get tested at the same merchants, used from the same IP ranges, by the same devices. Graph analysis finds these connections. The entities in the fraud graph are cards, accounts, devices, IP addresses, merchants, phone numbers, email addresses. Every transaction creates edges between these nodes. For example, card A is confirmed fraudulent. Looking at the fraud graph, card A was used at merchant X at 2 p.m. Card B was used at merchant X at 2:07 p.m. From an IP address that also appears in card A's history. Card B now has elevated risk, even if its individual transaction looks clean. That's a graph problem. If one node is confirmed fraud, nearby nodes in the graph become more suspicious. This is one reason fraud detection is so powerful. It does not just look at a single transaction, it looks at the network around the transaction. At companies like Stripe and PayPal, these fraud graphs are updated in real time. And they have to be, because by the time fraud is obvious, the money is already gone. If this is making sense, hit like because now it gets even more interesting. Then comes velocity checking. This is one of the simplest and most efficient ideas in fraud detection. How many transactions has this card made in the last 60 seconds? In the last 5 minutes? How many different locations has it appeared in? How many different accounts are using the same device or IP address? Fraudsters often test stolen cards with tiny transactions first. $1 here, $2 there. A few small purchases to see if the card still works. This is called card testing. Individually, each transaction may look harmless, but the velocity tells the real story. A card used 12 times in 4 minutes is very different from a card used once a week. A device opening 30 accounts in an hour is not normal behavior. Velocity checks catch the pattern that fraudsters can't hide. Now all of those signals, rules, ML score, graph signals, velocity checks go into the decision engine. This is the final layer that decides what to do. There are usually 3 outcomes. Approve, the transaction looks safe. Decline, the risk is too high. Challenge, the system is unsure, so it asks for 3D secure, OTP or an in-app confirmation. That challenge path is important because the model does not have to be perfect all the time. If the risk is ambiguous, the bank can ask the real cardholder to prove it's them. And that feedback helps the system improve over time. Every approved challenge, every confirmed fraud trace, every decline, all of that becomes training data. So the system gets better because it keeps learning from outcomes. And the whole thing has to happen inside that tiny 100 milliseconds budget. Rules first, then model scoring, then graph checks, then velocity checks, then a decision, all before the payment terminal times out. That is the real engineering challenge, not just detecting fraud. Detecting fraud fast enough that the customer does not even notice the system working. Fraud detection is like an airport security system. The first layer checks your boarding pass. That is the rules engine. Then you go through a scanner. That is the machine learning model. Then they check a watch list. That is graph analysis. Then they notice how many airports you have passed through today. That is velocity checking. Most passengers go through instantly. A few get pulled aside for a second look. That is exactly how modern fraud system works. If you found this useful, comment fraud and I'll make a full breakdown of the next layer. How challenge flows like 3D Secure actually work. Thank you for watching.